I don't know, without seeing you, you can also just give me an emoji or some feedback. So would you be happy to have a very, very basic introduction to neural networks, or would you say, no, let's start, I don't know, let's start already, we know the basics, let's start a bit higher, or we start with the basics and then we'll see how far we go? I don't know. Do you have them? Can we do emojis here? Or no, it doesn't work in Google Meet. Or to have some feedback.
Hello.
Yeah, combo, or if you can also talk.
Yes, I would suggest we start from the basics, but for the basics we can go a bit faster so that because we have some good background on it. Yeah.
Cool. Yeah. Because if you have a very good background, then we can do it the other way around, and you teach me.
Hello.
So,
Hello.
Yeah.
Okay, I would advise you also start from the basics and at least spend some time on the basics too, because some persons still don't really have the background. Though I have background, but some don't really have the background. So it be better others actually follow along.
Okay. Good. Then let's start from the basics, and then maybe I'll start from the basics on my side. So I'm Andreas. I don't know if you see my name, and I'm a mathematician. Like I did, funny enough, I did a PhD in machine learning in the last, was it the last century, the last millennium? So in the beginning of this one. So it was a PhD in machine learning, but in the field of mathematics. And I'm from Austria originally. I met Arun in Morocco. That's also an important part of the story. And for the last 10 years, I've been working a lot in communicating mathematics, also on the African continent. So we did a lot of projects in many countries. And so now I'm currently working a lot in communicating. Communicating means, like, I don't know, playing, teaching, doing outreach, not necessarily what you do in school, of research, and at the moment a lot of on AI. So there's a lot of communication of core mechanisms or techniques of artificial intelligence. My own field is reinforcement learning. There was an idea that we had with Yababel that we might do like a session on reinforcement learning at not today, but maybe next week or another day. I'm not sure how far reinforcement learning as a technique is important for you. I think it's one, like, these are the two, if you want to call them in a way, like neural networks and reinforcement learning are the two main fields at the moment, the two hot topics. And it's interesting because they would also merge. So nowadays you have this deep, the deep reinforcement learning networks. So it's like combining these two techniques. And my idea is to play with you. So I prepared a series of games and to look at basic concepts. So what is, I don't know, what is training? What are weights? How do networks, I don't know, get better? How much do networks understand? So it's more about the basic, but I think these basic concepts, which are not, they're so basic that they would go to all or to very many AI techniques. So understanding these basics would help you a lot in any field you're working. And yeah, I think, I don't know if you saw that gradient descent game, the boat game. So that's one game, but I'll start with one like an interactive visualization of a neural network, and I'm going to share my screen, and I'm going to share a lot of links with you. So I just paste, I don't know, let me see, do I have a chat window here? Boom, boom. No. Here, there's a chat window. By the way, if you have, cool. Maybe we can, now I see the chat. So whenever you have a question, just put anything in the chat. I think that's also good. For me, it's it would be nice to have, I don't know, any feedback. So if you give me a kind of, no, too complicated, or kind of, yes, great, then it's good for me. And I will look at and if you have any questions, just interrupt me. Feel free to really interrupt or comment or whatever. So I'll put a long link. It's a Google document that I prepared for you. So that's, maybe you can have it open in one tab, and I will tell you what to start and where to click. There's a lot of resources also for you to go deeper. And if you want to know more, and there are some online courses, neural networks for coders, or all types of, there's one link with a lot of books you can download. So I will go to the resources access denied. Okay, that's already good feedback. Yeah. Let me see. Oh yeah, I did it wrongly. So now it's good just to have feedback. Huh? So now you should have access. Try again, reload. Good. I'm going to start with the link number. Let me see. I put something. I'll make it red so you see which one I'm starting. I'm starting with one link further below. But I will share my screen too, so you can have a look at my screen. It might be a bit heavy to download depending on your internet connection. It's about 10 megabytes, that app, but I'll share my screen, and then you can, everything I show is available under open source licenses, so you can always, I don't know, even look at the code, play with it at home, or further use it. So I'm going to share my screen, and then let's start with that simple network. Let me see. I'll share my whole screen. I think that's okay. All right. So you can see everything. Can you see the screen? Yeah. Can you see everything? I'll start. So this is like one of the, they would call it the hello world example in neural networks, is to recognize handwriting. And there's an open database, a very famous one. It's called MNIST, MNIST, and that's a database of numbers. I don't know if you've seen that, but so they use it as a benchmark for a lot of training on neural networks. And the idea is I paint something, and then the network, I don't know, would tell me, okay, here wrongly, or right, this is a 2, or I don't know, this is like, now there's in the middle you see these confidence bars. So I'll do something, okay, and then I have full confidence that this is a 4. I can try a different 4. I don't know if you know this 4. Okay, that's also a 4, and then I can try a 7. I don't know. 7 is always a bit more tricky because you have different 7s or different 1s. So the idea is I do a handwritten number, and the network would recognize it. So what you see here is a typical already trained network. Actually, what you see in the center are the 10 output neurons, and the higher the value is, the more confident the network is that the number I give it is really the number, the real number. Of course, this is a trained network. You can try different things. You can try numbers that don't exist. You can also just, I don't know, do something like this and see, I don't know, why is it a 2? Or you can try, I don't know, a 3 upside down, would not recognize it as 3. Or I don't know, something, or see how the numbers would change. Now, let's look at the architecture of that network, and how does it work. So what I have is an input field of 28 by 28 pixels. If it's as I said, you know, it's I'm starting very from the basics. So if it's too, like, I don't know, if it's too boring, you just give me a sign. You just give me a sign. You're leaving.
I can see myself on your screen, so it's just interesting.
Yeah, okay. I'm switching back. All right, so you probably all have seen more or less a visualization of a neural network, but what's interesting, you have on the one side you have these inputs, yeah, and on the other side you have the output. So inputs here in our case is a field. Actually, it's 28 by 28 pixels, like colorful points, you know. I'll show you, let me just check here. I'll show you how it would look like. So if I do something, I enter the number 3 here, and it would automatically downsize the entry image to 28 by 28 pixels. You see, you have a certain, that's very important. I mean, for you working with data, I don't have to tell you, but you normalize the data. So if I start here, I don't know, I put the 4 in the corner, it would make it the same size, it would center it, and it would downsize it to 28 by 28 pixels. So whatever input I give the network, it would always make this kind of normalized 28 by 28 grayscale picture. Good. Now, that's the input. So I have 28 by 28. I think it's 768 input numbers. The numbers are gray, values of gray. So I give the network 768 numbers here, and something happens. We look at the details in the center, and at the end, I have this one of the 10 numbers that would spark and would tell me, okay, this is a 4. This is a non-trained network, so you have some random weights in the center. It would just tell me anything. I don't know. Maybe it's lucky, or maybe it's not lucky, but anything. It's not trained. So now the interesting part is, how do we train a network? So the first thing, we need training data. Here you can see a few examples, but I talked about this MNIST database. So it's 70,000 images. They were manually written, and each image also has a label. So it's not just the image. It's also, you know, it's a true. It's the image of a true, and it says it's a true. So you also have the true as a number. And now what I do, I take one image. I put it in a network here, for example, the number 9, and I tell the network this is a 9. I make it very slow. I give it another 9. I tell the network it's a 9. And the network itself would probably spark another number. So, for example, I give the network a 9. Here, in this case, it sparks a 9. I give it a 1. It sparks a 1. So it was lucky. But here it would spark a 9, but it was a 1. So there's an error. So there is a gap between what the network would tell me and what the real number is. And if there is an error, then I have to adjust the network in a way that at the end, for each training data, it would really tell me what it is. It would fit, like the output would fit to the input, to the label of the input. So I give him a 5, and it should spark 5. So of course, this is like at the beginning is a random number. I will now train it with a lot of images. So I put, I don't know, a couple of thousand images in here, and I would change the network. And it would get better. What's interesting here, you can see the 85% predicted accuracy. So what you usually do, if you have a big training set, you would not take the full training set for the training. You would take, let's say, 80% of the training set. So we don't take the 70,000 images. We take, I don't know, 50,000 images for the training. And the remaining 20,000 images I use for testing. So so it's the same basic material, but it's other images that I did not use for the training, and I use them to test the network. And that's what's done here. So so I used 3,500 images of the training 80%, and then I tested them on the remaining 20%, and 85% were correct.
Andreas, there's a question from Ilakura in the chat.
Ah, cool, perfect. Good. Interrupt me. Yeah. Okay. I'll ask you. Or you.
Good afternoon. Hello.
Yeah.
Okay. When you rescale the data, when you rescale the data, basically it will now be between 0 and 1. So how did the network actually recognize that, okay, this is a 4 after you have rescaled the number, because you are rescaling the pixels, right? And I think each pixel represents a particular number. So when you rescale this number to between 0 and 1, how does this network actually recognize, okay, this is still representing the same image after you have rescaled it?
Okay, I didn't fully get your question, but I think I know what you were asking. So I will repeat the question. So your question was about why, like one question, how do you get these numbers like between 0 and 1 or for the input?
No. Hello.
Yeah.
No, that's not my question. My question is this. Can you hear me, please? Okay, my question is this. After you rescale the data, basically when you wrote the other 4, the 4 that was like at the topmost part of the image, the algorithm actually rescaled the image back to the center.
Yeah.
So what I'm saying is, after you rescaled it, like when you rescale this stuff, like to be between 0 and 1, how does this algorithm actually still recognize that, okay, this is still the same image that you rescaled before?
No, the rescaling happens here just in a program where you give the input. So the data I have, the training data, is already rescaled. You see, this is just done here. For me, that's the extra layer where I give the handwritten input. The training itself is done on already normalized 28 by 28 pixels. So this would just I don't know, add this layer where I can do some handwriting myself, because this is like an extra thing that I tested the network on my own handwriting. The network itself is trained only on these examples. So what I do here, what I showed you, this is here I use the normalized data, just the 28 by 28 pixel data. Is this answering your question? Or?
Okay, thank you.
So this kind of extra that I can put my own 8 here, that's another thing, and that's maybe from this point of view is super interesting, your question, because at the end the neural network would also work with a number that I give them, and that's definitely this number as it is here. I don't know, this strange 3 is not part of the training set. So we're talking about one of the key properties of neural networks, which is generalization, that somehow happens, and we'll see later why or how, or get an idea how this can be. But for the training, so coming back to the training, I just train it with the data set, and I test it with the data set. So if it says here 86% accuracy, it's not the 86 or 90% on my handwriting. It's 90% on the data, on the training data that I give the network. Yeah? And I mean, here it's interesting. I don't know, I now have 10,000 images, so I'm around 90%. I don't get really a lot higher. So if I'm up to 94%, 92%, that's already a lot. And I don't know if we are happy with 92% accuracy. So on the training data, so some images from the training data would not work. They would not be classified in the exact way. So I don't know, here I don't have a training set, but let's say I take the 5 from the training, now it's a 5. Yeah, so it's quite okay, but it could also be something else. So what's important here to see before we go deeper is I have a training data. I can start from scratch, and I look, I give them an example. I look what's the output. I see what would be the real output. There's a gap. There's an error, and then I adjust the network in a way that the error is small, or the error vanishes. So I adjust the network. We're going to see how, in a way that it does what I want the network to do. So it recognizes the training data. What's interesting here is the network doesn't know if it's numbers, and if I give them any other training data, it would learn that any other training data. I could use the very same architecture just to learn letters, for example. Or if I have a training data which is bad, it would classify. If I give them, a 5 and I tell them it's a 6, it would just learn that the 5 is a 6. It doesn't know what is a number. It just, kind of approximates the training data as good as possible, 88% or 92%. So here in this, I would stop a second. So what's important at the moment is that I have a training data. I have a network, which is a kind of a mathematical structure, and that tries to, I don't know, I give them an input and it shows me the desired output, the output that I train the network. So so that, I think, from at the moment, important things to carry are training data, the network architecture. There's a certain accuracy on the training data, and then what we saw is also this kind of generalization. So it would also work, I don't know, with some strange number which is not in the training data. Maybe not perfectly, but yes, it recognized the strange, I don't know, 3 or the strange 4, which is probably not part, but it somehow, I don't know, has an abstract, I don't know, generalization way to recognize them. I'll show you, now we will go deeper inside the network, but I'll show you that this was one way of an architecture of the network. There are different ways. So you have, I don't know, you probably have heard about, you're going to see this, like hidden layers in the network, or newer, more recent network architectures called convolutional networks. So here you can change, for example, I can change, I don't know, a certain learning rate. I can switch between so-called optimizers or activation functions, and then I can do the same thing using a different architecture. And I might, for example, just use 2,000 images or 5,000 images and get higher in terms of accuracy than before. Now I'm already at 93%, for example. So convolutional networks in general work very well with classifying images, and I can get even higher. So now, if you compare it to the experiment we did before, we had, I don't know, 10,000 or 20,000 images, and we had 92%. Now I'm already at 95%. And that's interesting. So I changed some of the parameters or the architecture of the network, but I use the same training data, and I have a better accuracy. Good. I would stop here, and then we jump into a different game or app. Feel free to play with this example. You have the, I made the link red here. It's made for bigger resolutions. It's not yet optimized for any screen resolution. Here it says full HD, but feel free to play with it. Good. Is there any question or comment? Are you still with me, or are you happy? Is it then a difficult question? Huh? We sent the link here. If you look in the chat on top, there's a long Google document. Or in the resources channel. Okay, that's cool. So I show you. So this is like it's a long Google document with a lot of links, and I will not show you all of them, but we will play through some of them right now, like this one. And then I'll mark the ones that we played through in red, and then feel free to play with the other ones. I think we are going to go to the next one, but before this, I'll just show you a few slides. Let me start here. So that's now again,
Andrea, sorry, can I interrupt for a second? Yeah. Could you give an example of how this is used in the real world? So how on people's phones or on, I don't know, spam detection, how is this used in the real world?
The neural network.
Yeah.
It's, I think in almost all modern AI applications, you have a neural network. I mean, I don't know, be it any Alpha Zero game, chess game, be it in autonomous vehicles, be it in language processing, like any Siri, whatever. So yeah, I would say it's like the core technique. I'm going to show you a few examples, so you can now in the next app where I show you very basic examples, but of course the big networks, like for example, a month back there was a new language model. You probably heard about GPT-3 or like this very big language models. So and this would be a network which has 175 billion connections, billion weights or parameters to change. Here in this example, we had, I think it's about, you can calculate, so it's 800 here times 10, so it's about, I don't know, 8,000 or 10,000 parameters. If you take here the bias functions, I'll show you how the parameter change would work. But this would have about 8,000 parameters, and the new big networks that they use in whatever in industry, be it for image processing or for language processing, they would have millions or billions of parameters. So they're very, very, very big networks. But the concept is the same. So if I classify images, I give it an image here, it would tell me this is a cat, or I don't know. I'll show you like I give you input of a car, like the camera inputs of a car, and it will tell me the action I should take. Or I show you the, I don't know, positions of a Go game, and it would tell me, okay, now you play this move in any game. So yeah, I would say it's really nowadays almost all the, I don't know, call it the music recommendation, whatever uses neural networks. There are some other techniques, but generally nowadays it's really based. This is like core technology. Good. So I'll show you a little bit let's call it the formal or the mathematics behind such a network. just a bit. But so what we have seen, we have this input. So these are numbers. I don't know. Here we have 3 in our neural numbers. In the numbers example, it was 768 numbers. So, but this can be any amount of numbers. So it's a vector with numbers. And then you have so these numbers are connected to one or more, whatever, 1,000 or billions hidden layers. So these are, one layer is one kind of, let's call it a vertical vector. So here we have 5 so-called artificial neurons. So they're called artificial neurons, the dots here. So they're connected, and then you can have many of these layers, one or many. Like in the example we have seen right now, the neural networks, it was only one layer. So we had, I think it was 100 in between. So we had 768, 110. And then you have the output. The output can also be one or more, can also be billions of output. And these are all numbers. And each of these neuron, now comes the mathematical part. Probably you have seen this. So each of this, let's call it a blue dot, has input numbers. So here you would have, I don't know, the x1 to xt. So these are numbers. I don't know, for example, the pixel colors of my painted handwritten number. Then each of these numbers gets multiplied by a so-called weight. So you have x1 times w1, I1 for the I neuron, for the ith neuron. But let's say I get here number 1, I multiply it by, I don't know, any number 5, and then it gets into this so-called, they are all summed up, and you add another number. I'll do this quickly because I'll show you how it works. So you get a lot of numbers, they get multiplied, they get summed up, and then they get fed into a so-called activation function. Something happens with these numbers, they're truncated somehow, and then you get an output number. So whatever happens here, so you have these numbers, they get somehow multiplied, fed into here, and then they go away, and then here it can happen the same again. And at the end, so these numbers, at the end, they're multiplied, some numbers are added, and at the end you have another number. And that number, in our case, tells me it's a 4, because the fourth neuron would be very big. So I take the neuron with the biggest number with the biggest confidence in this way. So so this is it. I don't know if you see it the first time, it might be complex. I'll show you an example, but this is all the mathematics of a neural network. So numbers multiplied, something added here, one function, and then the number goes out. And this number then would be the input for the next neuron. So you, of course, if you have billions of them, it's a lot of multiplications and a lot of sums and a lot of activation functions, but that's all the mathematics. The activation functions itself here, that's an interesting part, because that's the nonlinear part in terms of mathematics. So here you would take a function that makes something strange with the number. Nowadays, the so-called rectified linear unit, this ReLU, is the standard function. You probably have seen this. So this is, in almost all the big networks, they use this ReLU function. And the ReLU function is a very simple function. So it's just the maximum between 0 and the input, which means if the number is positive, it stays the same. So if we give it a 5, it stays 5. If we give it 10, it stays 10. And if it's below 0 or 0, it stays 0. So I don't know, -5 becomes 0. -10 stays 0, becomes 0. And this function works very well. So you can imagine, I give it a number, I multiply it, I get here. At one point, the activation function would say, okay, if I'm below 0, it would stay 0. Elsewise, I give the same number away to the next neuron, and that's it. So now we'll jump into an example. So probably, I don't know, if it's the first time you've seen it, you might feel a little bit lost, but don't worry. We will look at it with real numbers. Okay, I'm looking at the questions. Yeah, what GPT means for general AI. Yeah, that's a good question. We can maybe later discuss. I'm not an expert in language models. And for the optimizer, okay. Let's look at the simple examples, and then we can see what are the different key components. I'll open, if you go here, I'll open the next one. Open the next app. It's called Simple Networks. So this is like an interactive kind of game where we can now play with the numbers. So It's not finished. We are still updating the design. So apologize for the not super beautiful colors and design, but in terms of functionality, it's already quite good. So what you see here is very simple. We have different levels here, so it can also go a little bit more complex. But we have very simple networks where we can change the numbers and look at the different numbers. So here, the yellow one would be my input neuron, and I can put any number or any number. I think it's between -4 and +4. So I give it for example, I give it a 1. Here I have the blue one would be the weight. I multiply that number, and then I have here an output. So this is the very, very simple level. So the level would be, can you find a configuration that just doubles my input? So of course that's maybe simple because I just multiply it by 2. So I have 1 multiplied by 2, and then I get a 2. And this would then of course work for any number, just because it's by definition I multiply it here with the weight 2, and I solve this first kind of game. Now if I have 2 input numbers, as we have seen in the example before, they would get summed up. So if you look at the let me see here. Here you would have a sum. So the W, this was the weight, the first number. And if I have more inputs, I would sum them up. So what I do here, I have the first one, I don't know, I multiply it by 1, let's say. This one, I multiply it also by 1. So it would stay the same. Put it on 1. So, and now I have an input here, an input there. Both are multiplied by 1, and they're summed up. So I get just here the sum of the 2 inputs. So this configuration, if I take the weights 1, I would just have the sum of the 2 input values. That's also a very simple example. So where just my output is the sum of the inputs. So you can see it's a network that just I don't know, makes a very simple calculation. It just sums up 2 numbers. I can do, and now that's the interesting part here with these games. I can do a lot of different functions. So I can, I don't know, have a network, a very simple one that calculates the average of the input values, or I don't know, only shows me positive values and not the negative ones. Here is the first network where I have a hidden neuron, yeah, and this one would have this so-called rectified linear unit. So here, if I give them a negative number, I just multiply it here. Either I put it here negative, let me see. But if I'm below 0, it would just say 0. You see, the target would always be 0. Or if I multiply it by a number which is below 0, it would just stay 0. So this was this rectified linear unit. I've shown you the activation function that just I don't know, changes my input into something below 0. So here I have, that's maybe, let me see. So this is already the full neuron. So yeah, here I don't have the weights. Let me see. So here I have everything I need. I have a weight, so I can multiply here. I have the activation function in the gray neuron, and I would have this so-called bias. This is this button here, which just adds a number. Can be a positive or negative number. So the bias, I don't know, would make that neuron stronger or less strong. If I add +100, it would make it strong. So even if a negative number would come in, it might become positive. So now the interesting part is that these little dots here, the blue one for the weight and the gray one for the bias, are my parameters that I change when I train the network. The activation function, what I told you, like this ReLU function, whatever, usually you fix it beforehand. So you have your network architecture, you would say, okay, I'm using ReLU. Most of the people are using this ReLU because it proved to be very, very good. And but and then I have my architecture, like I have an input, an output, but the weight and the bias I have to find myself. The network will adjust in a way that it does what I want it to do. Now here, that's, for example, a network that I want the network to convert Celsius to Fahrenheit. It's a simple function, but of course, neural networks can solve simple functions. They can also do complicated functions. If they can classify numbers, they can also, of course, convert Celsius to Fahrenheit. Now the question is, how do I have to put the weight and the bias so it will calculate that it would work for all input Celsius values, for example. So now, like here on the right side, you would have a simple visualization of training data. So 0 becomes 32, 10 becomes 50, 20 becomes 68. And now I'm already quite good. So if I put the weight here, more or less, I put the bias here, so I'm quite good. So it's almost, here you have an error. We can explain later how the error works, but the error is almost 0. So if I adjust it a little bit more, I can maybe make the network almost perfect. So now I adjusted these two numbers, and the network is trained. So now it's kind of almost perfect. I have a perfect Celsius to Fahrenheit converter by just adjusting these numbers. If the numbers are wrong, then it would not work. I'll make a stop here. So what would be the learning from this part would be that with this architecture of having input neurons, hidden neurons, and output neurons, and having this simple mathematical multiplying, adding activation function, with this kind of setup, I can approximate a lot of different functions. I can do this, whatever, Celsius to Fahrenheit conversion, but I can also classify images or do anything where I have training data and I want to do something complicated. But it's at the end, it's always the same type of architecture and adjusting weights, adjusting these weights and biases. And if they're in the right configuration, then the network does what I want the network to do. The network itself doesn't know what it does, but it just fulfills to find the to do something which minimizes the error here, the error on the training data. And depending on whatever I choose in terms of training data, it would find a solution. Now, how do we find these weights? And that would be the next question, where I can show you how do we adjust the weights automatically. That would be the learning part. So because of course in the real networks, like in the big one, look at GPT-3, you will never ever, even now with, I don't know, with 10 different or 15 parameters, you would not find the right numbers by hand. So you would need a method, an algorithm to find it automatically. And that's the learning part of such networks. I can show you here, for example, if you look at the Celsius to Fahrenheit, now it's wrong. I can add, it's called gradient descent. I can add that method, so I can just learn it. You will see that now it adjusted it on its own. I can go back, I can even, I don't know, take this off. It would always minimize the error to 0. Now I have the perfect network here. So I even have a 0 error. So this is a perfect converter for this training data. But funny enough, it works also for other Celsius numbers because it found the function itself. And you can also do it for more complex, I don't know, complex functions. Finding the maximum is already more complex. So here I can also, I don't know, train it. And now it's almost perfectly trained. Good, I'll stop. I'll look at the question. The added animation isn't interesting. Yeah, I don't know, feel free to play a little bit yourself with these numbers. And we are going to look now at the gradient descent. I don't know if you use this method. Gradient descent is maybe one of the core algorithms and maybe in all of AI, where you can adjust these numbers automatically, like the weights. Because the good thing, and that makes it also so powerful, is that once I have the training data, of course, I have to find a certain architecture. I don't know, that's the tricky part. That's still a manual part, and that's a lot of experience, like how many hidden layers do I take? How many neurons do I need to have good data? But at the end, the training is automatic. I just feed in the data, and the updates of the weights, that's done by this gradient descent algorithm. So I don't have to do anything. So now it will just find a good solution. It might get stuck in a local minimum somewhere, or it might take some time. So here, I don't know, but maybe I have to I don't know, move it a little bit, but at one point it would find a quite good network that does what I want the network to do. I'll stop here for a second. Let me see. If the value for that neuron is above 0, pass it. Exactly. So Kevin, that's exactly what the relo function does. So I mean, if you look at the mathematics.
Hello. Can you explain the relo very well? Like I didn't quite get. Like okay, if the value is above 0, what will happen?
So if the input number is above 0, it would stay the same number. So if you give this neuron a 5, it will stay 5. If it's below 0, it will just become 0. So this means, I mean, if you look at it in a more philosophical way, that because these networks are also kind of copies of whatever what we might have in a simple form in our brain. Our brains are more complex, you know, but it means that if there's a positive signal, it will stay positive, and if it's very positive, it will stay very positive. You know, the higher the number, it stays equal. But if it's a bad signal, it would just vanish. It would just disappear. It would just be in 0. So as Kevin writes, it doesn't pass. You know? And that's if you look here, I don't know. Let's look at a simple. Here we have it. So I'll stop it here. So if it's big, no, it goes and it stays big. But if it's below 0, it doesn't matter. If it's very bad, it would just say 0 here. And it proved to be a very, very good activation function. There are different activation functions. Like in these relo functions are quite new. So in my time, when I did AI, like 15, 20 years back, most of the time they used the sigmoid functions. So it would, even if it's very high, it would stay big. And if it's very low, it would be low. So it doesn't have this kind of going further up. So here it's really, if it's very high, it would stay high. You know, it's just mathematically, it's the maximum between 0 and input and x. Good. Let us have a look at this algorithm, how to find the right numbers, the right weight, the right bias, the right parameters.
Hello. Yeah, please. I'm very sorry. Can you explain bias and weight?
Yeah.
Like why do we need to add the bias and what part of it?
Yeah. Okay. So let us look. Maybe we can have an example here. What happens? Yeah. So what happens if I have a high bias? This input signal would become very high. If the bias is low, sorry, not the bias, the weight. So if the weight is just 1, it would stay the same. If you look at the blue, I don't know if you can zoom in. So I don't know. You can look at the blue river. So if I have a high weight, I will just multiply it. So it will get higher. If it's low, I can make it low. So I can influence the strength of that neural connection. And this means if the weights are very high, that connection is very strong. And in terms of, if you interpret it, for example, in terms of the pixels, which we have seen here in the neural network game, so you would say if that pixel, let's say it's this input, if that pixel is very strong, this means that pixel is very important in a way. So if the weight here would be very high, because pixel on that side would mean it's probably a 3. And if there's no pixel, I don't know, let's say in that area, there's no pixel, then it's probably an 8. So so it maps it, the weights are very important to give a strength or anti-strength, like weakness, to certain input nodes. And the network would find itself, trying to fulfill what the training data tells it, the best weight configuration. So which input is very important for which output, and it would adjust it in this way. So here I would make it strong. So that's the weight. The weight it's a number that I multiply. So I can really make it very strong. With a high weight, I make that connection very strong. The bias is different. The bias would apply. Let me see if I have an example. I have several inputs. So here I have 2 inputs, and the bias would always apply to the whole neuron here. So this means to the whole sum of inputs. So I get this input here, I get this input, and then I would just add a number. It's not multiplied, it's just adding a number. And the bias would just make all the inputs of that neuron stronger or weaker. You can imagine, now we have this ReLU function. So whenever there's something below 0, it will just become 0. But if, for example, I give that neuron a high bias, the inputs can even be below 0, because the bias, since I add a number, so the sum, like the input here plus the bias, would be below 0. So the signal would go through. So with the bias, I can make certain neurons, all the inputs of a neuron, stronger. So here in the example, I would say, okay, it's not just one connection, but it's all the connections going to one neuron, and I will give them a certain strength. So if you look here, the weight is for one connection, but the bias would make this whole neuron. So all the connections coming in here, they're already weighted. And then I would say, okay, this all together is important for the activation function and for the next output. So it's a different, I would say, it has different characteristics to add a number to all the inputs, not just to multiply here each individual connection. The problem, and here we're already starting into going into a very difficult field, is like the interpretation of this network. How does the network know which pixel is important? Why should this bias be higher than the other one? And that's something going into a field called whatever, interpretability or transparent neural networks, that I understand what's happening in here. But that's a relative new field, and it's not clear at all why. I don't know, why is it this neuron that has this weight that has to be high, or why is this biased that way? We don't know, and that's also what they often refer to as a black box. You know, I have this neural network, the numbers are adjusted, I don't know. I mean, it learned it somehow, but how should I know that this, I don't know, this bias has to be high here and this weight here, and depending on the architecture, maybe the weights are completely different. But at the end, what is important that whatever I give the neural network, it works in a way when it's trained. Now it's not trained, this one. Was this somehow like a reply? Do you have any further questions?
Yeah. Hello. Yes, I've sent the message in the chat box.
Okay, I see it. Yeah. So the question is, if we always have to specify a bias, or the network will set it at random. So when you start at the very beginning, so before you start training, so this is a good example, you just set everything randomly. There's a lot of science how this random could look like, or what type of randomness is better for starting networks, but it doesn't matter. You set them randomly. So you set them randomly, and then you train it, and then it would just adjust the weights and the biases in order to have like a minimal error between the training data and the output of the network. That's very important, to minimize that error. So if I look here, this, I don't know, let's look at the example with the Fahrenheit. Where was it here? So now with this configuration, let's say with this weight and this bias, I have an error of 5. So it's really bad. So this doesn't work at all. But if I adjust it a little bit better now, I don't know, I still have a bad error, but let's say I train it automatically. Now the error is 0. So this is like a perfectly trained, so this configuration, I have this weight and this bias, it's perfect. And there could be several ones, it doesn't have to be exactly this one. So it can find other ones. But with these two numbers, this network now does exactly what I want it to do. It converts Celsius to Fahrenheit. And the training was done automatically. The only thing I have to give the network is the training data. And I define, so I defined an architecture. I put something on random. I put these on random, put it somewhere. I put it very low. Let's see if it works. And then I give this training data, and then I just start learning. No, it's a bit lost here. So sometimes it could also get stuck. We're going to look at this right now in the next example. So now it found it, and the network is trained. I'm going to jump to the next example. And that's I don't know if you've played this game. I'll make it red here. It's called gradient descent. That's the algorithm I told you that adjusts the weights and the biases. And let's open it. So that's now, like, it's an abstract game, but it really visualizes very well how you can find that that minimum. How can you minimize the error? So the idea here is to find the deepest spot in the ocean. So you have this kind of boat, you have these probes you can send down to the ocean floor, and whenever you send a probe down, the feedback you get is a small, I don't know, small slope. That's the feedback, you know, like the floor on this certain position is, I don't know, this type of slope. And there's a treasure. You know, that's the game. So there's a treasure on the deepest spot of the ocean. Now I found it. And the question is, how do I look for this treasure? So that's maybe something, if you play, you can try to find out yourself. So I put a few probes. I look at the slope, and then yeah, I can see here it's going down. Then I will probably just follow this down. I will try here. Oh, okay, there was nothing. So it's not here. Oh, it goes steeper here. So that's a good example. I found this one here, and this could have been the deepest spot, but it was only a local minima, you see, because there's another more global minimum here. And what you see, this function below here, you could interpret it as the error function of the network. So the error function, I want to minimize it. I really want to find the minimum. Ideally, the error is 0. So let's say the treasure is here on the point 0. So when I found the treasure, then I found a position of the network, of the weight, that makes the error 0, which means the network does exactly what I want the network to do. And the position of the boat here, in this sense, it's just left and right. This could be just a number. So the position of the boat would be my weight, for example, or my bias. It would just be a parameter. And then I have some feedback on certain parameters. I'll explain you a little bit how this works. So I get some feedback, and then I try to go down with the gradient, with the slope, in order to find the steepest point. So now I found this one. I found the treasure. So you would always go further down, and ideally you find the global minimum, which minimizes the error, and the error is 0. And now this you do with all the weights of the network. So here in this example, this would be like a one-dimensional network. So I have only one weight that I adjust. So it's the boat left or right. And I have to find this one position where for this weight, the error is 0. So if I find it, then the network is good. And in large networks, as I told you before, I do this boat treasure hunt, but for 175, whatever, that's the GPT, the biggest model so far, 175 billion parameters. So you have this boat game, but not in one dimension, but in 175 billion dimensions. And but the method is the same. So it's still this gradient descent. I get some feedback. I know it's going down somewhere, and I try to go always further down. And once I found this configuration of all the weights, like the boat position in all these dimensions, then I found the configuration of the network which has the least error and does exactly does what I want the network to do. Good. So I don't know. I'll look at the question. Do you have a feeling now how networks work, or is it more complex than before? I don't know. Or do you have a question? Maybe you can then can do a quick summary on the different ingredients. I don't know if some of you already played with neural networks, and this might not be anything new for you. So, but the most important thing is here that you have a certain architecture of the neurons. It's just numbers going through, and then you adjust this. You adjust the weights and biases by this gradient descent algorithm. There are different versions, but basically it's just trying to minimize the error function, and you do this automatically. And at one point you have this network configuration, which just fulfills what you want it to train. The network doesn't understand what is trained; it just tries to have no error. And the error is like it has an output, and the output should be what is the training data. Okay, so I don't know. Maybe you give me some feedback, or if you have a question. There was this other GPT-3 question, but yeah, feel free to ask, or let's discuss.
Thank you very much. Like the way you just explained it to the animation actually made it very clear. Though I had some interactions with neural network, but I didn't quite get the understanding like that until I saw your animation and stuff like that. It's actually fun. Thank you very much.
Mm-hmm. Any I don't know, any other feedback? Do you think that it's a bit more clear how this neural networks as a technique, how they would work? What I can do is
Hello. Hello.
yeah.
Yeah, I have a question. Are you still going to talk about this gradient descent? Because I wanted to ask, like, let's say for instance, now you have a loss function. After you have done your iteration before one epoch, you've gotten your loss function. So, like, I don't know if you're still going to talk about it. How does the network actually reduce this loss function? Like, how does it actually propagate back into the network and say, okay, these are can shift this weight and bias and stuff like that. So I don't know if you're going to talk about it. If maybe.
Yeah, I mean, it's like the basic. I just open up here to see it, that you can see a network. Like, of course, if you start here, I have the output. Like I have like the network gives me an output, and I have the output of the training. So there's a gap. Let's say there's this difference in terms of slope. So if I have that slope here, I can adjust that weight. Like the next weight, because that that weight, or all the weights that change this number, I have to adjust them. I make them higher or smaller. But then I get another output here, and this output I have to adjust towards the next one. That's what you call the back propagation. So you do this like the changing of the weights. You have to do it from back to the beginning, and you always have to check. It's like iterative. You always check the last part. There's a gradient on that, and I change it towards the gradient. So if the gradient goes down, I go further down. If the gradient goes up, I go further up. And the steeper it is, the smaller steps I do. It's a little bit like the boat game. But I start here, and then I do it back. I have a very good reference. So if you look at the list here, here it says neural networks. I don't know if you know this YouTube channel, 3 Blue 1 Brown. These videos here, they show you exactly how this backpropagation works. So so what they do, it's not interactive in a way that you can play with the networks, but they have very good animations, and then you would really see how the backpropagation works, how this gradient descent would start at the end and then jump like from one to the other. I cannot explain it better to you. I mean, the best way would be to program it. So if you program it, then you would easily see how it works. Also, how the iteration would work in terms of going back. But these animations are very, very, very recommended from my side. So if you want to look at these videos, they're very good. It's like a total of 1 hour, and they would really they also take this example of the neural numbers, and they show you this network. But now they show you the numbers, how it gets trained. So that would be the backpropagation algorithm. There are a lot of details, of course, if you look at it. The gradient descent, for example, nowadays they call it stochastic gradient descent, which is a variant. So they would not calculate the gradient on the whole training set, because that's a lot of calculation. They would just take a sample. I don't know. I take 20 and not the 5,000 training data that I have, and then I would calculate the gradient on that 20, and then do my update of the weights with this probably one gradient, but it's still not bad. And I always take 20 random examples, so that's why it's called stochastic gradient descent. So it finds the treasure, but in a more not that direct way. So it's a bit more strange that I go down, but it's faster. So at the end, it's also a question to train such big networks and to do this gradient descent algorithm. That's also a question of speed. That's why you need good graphic cards and a lot of computers. maybe talking about resources. So if you look here in terms of resources, there's a very simple. I don't know if you after doing your 10 academic course, you still feel like learning something. There's this elements of AI. It's a very simple. I would call it a I don't know, an elementary AI course, but it's very well done. And I don't know if there's probably also a French version, definitely English version, and it's very good just to introduce different techniques of AI on a very basic level. So there's a lot to read. They have some questions at the end of each article, but that's very good. And then there's some AI courses. There's one, I don't know if you're a little bit into coding. Let me see. There's one which is quite good. This fast.ai. So it's a deep learning course for coders. Of course, that's I don't know, more complex, but it starts with a very complex network, and it would tell you in a modular way how it would work. So you would see similar things as today, but on a real life coding example. So that's also very recommended. This course.fast.ai. There's a link. This one, that's I would call it a semi-legal link, but it's a GitHub repository with a lot of books, and that person, I don't know, I think he's from China, or she put a lot of books in here. So you have I don't know, courses and books, and you can just download the PDF. So some of them are I don't know, you would need to buy them if you want them legally, but there are some very, very good books on machine learning, deep learning, AI here, NLP, natural language processing, that you can just have the book, and these are the big classics. So if you're interested in further reading, feel free to dive into these resources here.
Hello.
Yeah.
Hello.
Yeah.
Are you through with your talk, please? Like, is this the end?
Sorry? Yeah.
Are you through with the talk?
Sorry,
Hello.
I cannot really hear you well acoustically. Yeah.
I want to know if you are still going to continue with the lecture. I wanted to ask a question.
Can you maybe type it, Ilekura?
Hello. Hello.
Type your question, because I didn't get it. So it's about how we continue with this lecture, or I didn't. Sorry that I didn't understand it. Do you want to just to type the question, and I can answer the. So I mean, for me, yeah, I will stop the session here. Exactly. So that the idea was to have a 1 hour session, and but we can do. I'm open to do another hour. I don't know, in the next weeks. Also for example, on this reinforcement learning, on another technique. And yeah, feel free to ask any question.
Okay, I was introduced to some courses, and I got to know about L2 regularization and L1 regularization. So I don't know how does, okay, basically when I was reading about it, I was told that during trading, and then after getting the loss, the algorithm will try to penalize the layer. Take for instance, I'm using TensorFlow, and then I'm using kernel regularizer. That means it will actually apply to that layer. So I don't quite get how the algorithm will actually penalize that layer, because if you're adding the loss, like if you're using L2 now, maybe you have quantified the weight and everything, and then you add it to the loss function. So how does the algorithm actually know the layer to actually penalize? And okay, this is the layer I have to penalize and apply this L2 regularization on. I don't know.
So I don't know if I got the question fully, but the idea was how does the network know which layer is important, or which neurons have to fire, or how maybe it's a little bit in this direction, which parts of the network are important, or how do you train somewhere in between the network?
No, that's not my question.
Yeah.
My question is about regularization.
Popularization.
Okay, let me.
Yeah. Maybe you can type it. The regularization. Okay. Yeah. So so that you make sure that a network is well regular. That's something that I think you need a lot of practice in terms of setting up a good architecture. But I'm not a, it's interesting. I'm not experienced in applying these networks. For me, it's more like I understand the mathematics, so it would be the question of how can you, I don't know, guarantee convergence. But yeah, I don't know. Yeah, maybe you can ask your question again. Yeah. Have you used neural networks for like to analyze something or for some application?
Hello.
Yeah.
Can I ask a question?
Yes, for sure.
Okay. Basically, like what I'm asking is this. Take for instance, you're applying L2 regularization. I don't know, can you hear me?
Yeah.
Okay, on a particular layer.
That I still don't get the question. What, on a particular layer, that you apply regularization on a particular layer? And so that's the question? Or? Yeah, we can also have a one-to-one talk or whatever. So I'm sorry that it's difficult for me to understand the acoustically. There's a lot of noise interference. Okay, so I would say from my side, I would leave it here. Feel free. I can give you. I don't know. I'll give you my email address also. I don't know if you want to contact me or have any further question, and we can easily. I do a follow-up session. I don't know, next week or in 2 weeks. And to see more things. I'm also happy if you give me some feedback in terms of, I don't know, was this worthwhile? Did it make sense? Did I understand something? Was it, I don't know, can I do something with this information, or was it just, I don't know, a general thing? So it's also in terms of, if I do another presentation here with you, then I can adapt the content in a way that it's more suitable to your needs. So feedback is more than welcome.
Hello. Yeah, we need more animation from you, like basically something that can actually show us what is actually happening and which you have actually done. I think the next meeting or the next lecture, you can actually incorporate that into the lecture. It's actually fun. And you actually tried, to be honest, you simplified neural network to the barest minimum. To be honest, I actually gained a lot from this session. Thank you very much.
Yeah, you're welcome. Thank you. Thank you for the feedback. Good, then yeah, good luck for your course, and I hope to see you very soon again. And I'll bring a lot of more animations and visualizations. I have a nice simulator that I can bring next time. Okay. Bitte, Stephanie. See you then. Bye-bye. Cheers.